Good morning, everybody. I'm very impressed with the turnout given the festivities last night. So thank you very much for. Were you going to do something about the feedback? Thank you. Okay. Thanks everybody for coming, and we're going to talk to you today about some best practices for configuring, securing, and monitoring your Amazon CloudFront distributions. Very privileged to be joined by Cherie Wong, Anton Radlin, and Efren Fuentes, who will be giving you some of those details. I'm going to start by giving you a little bit of context regarding how CloudFront delivers content and some of the terminology that we'll use throughout the presentation, and give you a little bit of explanation about just how some of our routing works. Cherie will talk to you about configuring your cache on CloudFront. Anton's going to discuss measuring your performance with real user monitoring, and maybe we shouldn't be talking about RUM this early in the morning, but we're going to go for that anyway. And finally, Efren will be talking about stopping malicious viewers with CloudFront and the AWS WAF. So before we get too far into it, I want to tell you a couple of terms that we use within CloudFront and just what they mean. So when we're talking about a viewer from the CloudFront perspective, it's basically we like to think of it as a person, but ultimately it's a device, generally on a consumer viewer network of some sort, such as in the US Comcast or AT&T Mobile. So it could be a mobile device or a desktop, some sort of internet-connected device like a smart TV, or an increasing number of IoT devices. So that viewer is kind of the consumer and the end consumer of the content. The idea is that it's not content then going to some other thing, and when the content gets to that device, it's being rendered, processed, downloaded, used, what have you. Our CloudFront POPs is our network of 68 edge locations spread throughout the world, located in data centers in major metropolitan areas. These differ from the AWS regions in that the whole point of a CDN, of a CloudFront POP, is to be close to other networks and other viewers. So by definition, those POPs need to be in cities and generally in high-rise buildings, right next to where all sorts of other carriers have their equipment, so we can connect to them and deliver content to your viewers as quickly as possible. In physical terms, they tend to be several racks of servers and network equipment, and they are the actual endpoint that terminates that viewer connection. So when your viewers are connecting to CloudFront, they are actually having that connection terminated in one of those locations in a metropolitan area, such as in Atlanta or San Francisco or Chicago. So each of these locations is more or less identical, and the idea behind a CDN is that the location that you pick it's relevant from a performance standpoint, but it's not relevant from a content standpoint. So whichever location you pick, you want to pick the one that provides you with the best performance, but they all look the same in terms of the services and the content that they provide. But that location selection is critical, because from the viewer perspective, as I said, minimizing the latency and maximizing the throughput is imperative, and that's a lot of the work that we do at CloudFront. We have multiple teams dedicated to just figuring out how to consistently get that content delivered by the best POP for each individual viewer. And we'll talk a bit about how we make those decisions and why sometimes it seems like we make a decision you wouldn't think would be intuitively obvious. From the CloudFront perspective, obviously the customer experience is of paramount importance to us. But in addition to that, availability is our second priority, only to security, which is for all of AWS always our top priority. But in the event that a location is unavailable, we want to quickly make sure that viewers are routed away from that location to another location. In addition, we're able to manage capacity. So in certain metropolitan areas such as New York, I believe we have four edge locations. So being able to detect, saying, well, this particular location in New York might be busier, so being able to move traffic between locations is critical in terms of managing our capacity and maximizing that customer experience. And finally, location. We'll talk a bit more about how location factors in, but the location is clearly important. So we talk about routing, and routing can mean multiple things depending on your context. If you're a network engineer, routing generally means packet routing. Packet routing, I don't like to call it dumb, but it's very simple. It's designed to move huge volumes of traffic very quickly and be able to make decisions at terabit speeds in a very small physical footprint. So basically, the only thing it takes into account is a destination address. So if this is our viewer, and this is CloudFront, and this is the CloudFront address that you were given, and this is the blob known as the internet, the client is basically saying, I want to connect to this address, and the internet takes care of just routing it there. There's no notion of capacity management. There's certainly manual actions that network engineers can take and some coarse capacity management, but generally speaking, a link could be entirely congested, and the network will just keep on trying to cram packets down it because it doesn't have the context of the full path to be able to intelligently manage that capacity. That's just not the way the global routing algorithms work. So, but how do you actually get this address? Because these IP addresses, we see them as software developers and engineers, but we never want to expose that to our viewers directly. And this is where request routing comes into place. And this is, again, when we're talking amongst the CloudFront team, because within Amazon, the actual network engineering team is separate from the service team, which is CloudFront, that manages the application on top of the network. The vast majority of the time we're talking about routing, it's request routing. And in those cases, we are able to do, because of the fact that that happens at a higher layer, we're able to take into account the latency of the end-to-end path, the throughput that's available, the capacity of our locations in those regions, as well as the geography in the event that we don't have some of those other metrics available. It's generally done at the DNS layer or potentially higher, depending on the application. So in practice, what this looks like, excuse me, is you have a viewer, and they will do a DNS request. Now, I've simplified the DNS lookup here, but what happens is that the customer will ask for, or the viewer will ask for customer.com, which will then go to their ISP's recursive name server. That will then eventually contact the CloudFront fleet of DNS servers that actually is part of our Route 53 service. We make heavy use of Route 53 as part of CloudFront. This server will decide, based on some information we'll talk about in a minute, which address. We're using that notional address of 1.1.1.1, which then gets passed back, cached for a certain period of time in this server, given to the viewer, which then uses that same path, that packet routing logic we talked about to actually get the content. So first of all, it figures out which address to contact, and then it uses the internet packet routing to actually get the content. But here's where things can go a little bit sideways sometimes. So if we have an example user in Chicago. Now, both from a geography perspective as well as a speed of light perspective, and assuming that there's in the normal case, we would want a user in Chicago to be directed to one of our Chicago edge locations. Makes perfect sense. But in this case, the viewer, sorry, I should have made that viewer, that's my mistake. So we're talking about a viewer here. The viewer is, their ISP's DNS server is actually in San Francisco, right? So what happens is the viewer asks the ISP's DNS server for customer.com. That request then goes to the Route 53 infrastructure. But the Route 53 infrastructure doesn't see the customer's IP address. We can't identify what that customer is. What we see is the ISP's DNS server. So we say, hey, great, we've got locations in the San Francisco area. We send the address of one of our Palo Alto locations. So that goes back. The IP address goes back to the viewer of the Palo Alto location. And now this viewer in Chicago is getting a higher latency experience than they would otherwise because they're talking to that edge location in Palo Alto instead of the one in Chicago. So what happened? This is what we refer to within CloudFront as a divergent resolver. So ideally, and many ISPs do this, but there are situations where in certain networks and certain types of footprints, you have a wide distribution of viewers using a DNS server. It might be across multiple networks. It might be across multiple geographies. But it results in this kind of suboptimal routing. A common example of this is the distributed corporate network that might, for example, have a lot of their infrastructure in, Seattle, which might result in all of their requests when they're in Vegas being served out of Seattle. I don't know, just a random example. Anyway, what can be done? So the obvious answer is to use a local resolver. But given that many of you, like we have, hundreds of thousands and millions of users, getting each of them to change each of their connections may not be practical. It could be. It depends on your application. That could be a practical application. But another option is to use a resolver that supports the EDNSO client-subnet extension. There we go. So this is an extension that was developed, several years ago. And the idea is that, that it uses the EDNS extension protocol as part of DNS to provide a portion of the actual client IP request, the IP address, so the subnet, so the /24 subnet of the viewer requesting the address. No client-side resolver modifications are necessary. This is purely an extension that exists between the ISP's recursive resolver and the CloudFront Route 53 authoritative servers. Some common open resolvers, such as the Google 8.8.8.8 Anycast resolver, support it. And so in those cases, if you do have customers who have that problem, you can transfer them from that previous state of affairs to this one. There we go. So again, you have the viewer in Chicago, who's in the Chicago Edge location, and they hit the Google public DNS. Now again, that server may not be in Mountain View because it's Anycasted. We're not really talking about Anycast here, but the point is that it's a DNS server that supports ECS. So now that DNS query may come from Mountain View, California, but it includes the subnet of the IP address of this user. Now, we make a large number of latency measurements on a very regular basis from a lot of properties, including the Amazon retail properties, where we constantly measure performance based on these the traffic from customer from viewer networks. So we have a huge corpus of data in terms of which POPs perform, which of our locations will perform best for which viewers. So based on that, we are able to look up that subnet and say, okay, well, this came from Mountain View, but actually we know this user is in Chicago due to ECS. So then that bubbles all the way back. It sends back the address of the Chicago POP, and now the user is having this nice low latency, high throughput connection to the local network, to the local POP, as opposed to going globally, going to California. So fundamentally, the key takeaway here I'd like to leave you with as we get to Cherie talking about configuring your distribution is where you're routed depends on a number of factors. Your network, your geographic location, as well as the status of our individual locations. DNS is an imperfect mechanism for this. These kinds of problems, you would say, why would you use DNS? The ubiquity of DNS as being in literally every device out there is a really challenging a benefit to overcome. So we put up with a lot of challenges because of it. But if you do have customers who are having routing problems, getting them to use ECS enabled resolvers, will significantly improve their experience. And with that, I'd like to hand off to Cherie Wrong, the Senior Engineering Manager on CloudFront. Thanks, Cherie.
Good morning, guys. So the first question I have for you guys is, why would we cache? Our whole raison d'etre for this is what I call, or what I'm going to give you as two laws and the two themes that will resonate throughout my presentation. The first one is we want better performance for your viewers by serving it from our edge locations. And number two, we want less load on your origin. So what should you expect? Most of you have probably used CloudFront or CDN. I wanted to show you how we cache, what we do with viewer requests, and how you can dictate what we cache and for how long. Then we'll talk about a couple of best practices. First of all, Alex was mentioning we have 68 edge locations, which I've kind of put only a couple of them on the bottom of the screen in green. All of these edge locations or points of presence, or what we call POPs, have to reach your origin for your content. The blue layer here is something that is new and that we just announced this week. We've created regional edge caches. Part of the reason we did this is we were getting a lot of customer feedback around, as your network is growing in terms of the number of POPs you have, I'm getting more and more hits to my origin. And that violates our law number 2 that we just mentioned. And so we created these regional edge caches where multiple edge locations will now go into one of 9 different regions, which will then make requests to your origin. So this means viewer requests that are coming in, if it's the first time we've seen those requests and the object is not in cache, they will then ask our regional edge caches for your content, which will then send 1 request to your origin per regional edge cache. So in this case, instead of having 8 different requests to your origin, you now just get those 2. So what happens within each edge location? Well, first of all, when the viewer request comes in, we ask a simple question, is it in our cache? If not, we have to go and fetch it from your regional edge cache and your origin. If it is in cache, is it expired? If not, fantastic. But if it is, now we have to go and revalidate with your origin. So we're going to send a conditional get to your origin, and if modified since, or if none match, depending on if you're using last modified or an e-tag. Your origin will respond with a 304. It hasn't been modified. Go ahead and serve it out of cache. Or a 200, and here's the new object. We'll cache it, and then we'll respond to the viewer. So let's talk about this green box a little bit. How do we actually cache? Or rather, how do we generate a cache key? We used your host header, your d123.cloudfront.net, or your cname, example.com, to create a canonical URL. You remove all the query strings, the protocol, and add the accept encoding header, which effectively filters down to gzip and identity. For every single object, we create an individual cache identity key, which is your canonical URL and all the very parameters that you specified in your cache behavior. We'll talk about that in a second. Every object, we have hierarchical cache keys. So we also have a base cache identity key, which is a hash of your d123.cloudfront.net concatenated with the accept encoding header. We do that so that when you ask us to invalidate objects, we can easily go and invalidate all the variants of that object as well. So how would you tell us what to cache and for how long? You can use the expires headers. This is part of HTTP 1.0. We do honor the expires header, but it does come with a couple of different gotchas. It's a fixed point in time. The accuracy relies on clock synchronization. And if you're using an S3 origin, it's typically a value that was set by somebody when you when you first uploaded the object to S3. So you can actually have a last modified date that is after an expires date. And so those are a couple of different things that we warn about, and so it may not be something that you necessarily want to use. More importantly, most of the time you want to invalidate or you want to have an object expire in a relative point of time from when the viewer actually asked for it. And so that brings us to cache control. You can set cache control directives that give you much more fine-grained control over exactly what is cached and for how long and in which location. So if you were to set max age, which is in seconds, so in this case 300 or 5 minutes, we would cache that object for 5 minutes, and also the browser can cache that object for 5 minutes. But if you think about max age and smax age, the smax age will apply to the shared edge cache, or essentially CloudFront, and max age will apply to your browser. So you can actually have a browser cache for a different period of time than CloudFront. This is specifically useful for customers like display ad, for display ad use cases. So you may not want the browser to actually cache your ad, and because you want to actually serve it from an edge location and be able to get a count of exactly how many times it's been rendered. So in this case, you can set max age to 0 and set the smax age to a larger period of time, or in this case, 1 day. You can go to your CloudFront access logs to know how many times that object is served, but you don't have to hit your origin. And so here are a couple of examples of what you could set cache control headers to. If you have static assets or media fragments that don't change very often, you can set it to a very long period of time, or in this case, 1 year. If you have live streaming manifests, we're going to talk about dynamic content in just a second, but you can cache it, and you can set that cache period to be something that's very low, from 0, 2 seconds, et cetera. And lastly, when you're thinking about login landing pages, you can still cache those assets, and in this case, what we've done is we've said, if you have a cookie set such that you have some user information or a session ID, don't cache it, but otherwise cache it for 30 seconds. The set cookie is also important because it tells CloudFront to strip the cookie header so that you don't run the risk of leaking session IDs across users. Dynamic content. Most of you will think dynamic content is really not cacheable, but it is, and we want to reduce the load to your origin, law number 2. So in this case, what you can do is you can set no cache or a max age of 0, which essentially means we'll cache it, but every single time we get a request for it, we will send that conditional get to the origin. Is this the latest object? If not, please send us the latest one. This will reduce the load to your origin, or the amount of times you have to transfer that data from your origin. And if you do have content that you don't want stored at all at a CloudFront edge location, you can use no store or private. The difference is private does allow your browser to cache that. So now that you've seen how we cache, how you can control it, how do you manage it in CloudFront? You can create cache behaviors. Cache behaviors are different cache configurations that are based off of the URL file path. Or in this case, I have a screenshot of those going through your, or requests coming through your images file path. And so you'll see at the bottom, hey, we have some minimum TTLs, maximum TTLs. How does that work with max age and smax age? If you set max age and smax age or expires in between our min and max, we'll use it. If it goes outside of the range, your cache behavior takes over. And if you don't specify max age at all, we'll use the default TTL that you specified in your cache behavior. So a couple of different tips that we wanted to share with you. The first one is we do cache errors that are coming from your origin. We get overworked, and sometimes your origin will get overworked as well, and it needs a break. So what you can do is for any error that, or any HTTP error that is coming back from your origin, you can set a custom error page. You can change the response code, and we can cache that for a certain period of time. So in this case, if you're getting a 404 error page, or a 404 error from your HTTP, from your origin, it may mean that there's a bad link out there, and you don't necessarily want your origin to take that load. So you can have a custom error page, and you can set this, we can cache that response for a longer period of time, or in this case, an hour. But if you're getting a 504 or gateway timeout from your origin, you can set that caching time period to be much lower, or as much time as you need your origin to recover. For example, 1 second or 10 seconds. The default is 5 minutes, and what we've noticed is that for customers that have very real-time data like media streaming, they want to set that TTL to be very low, like 1 second. Next tip, version your assets. While CloudFront supports invalidating objects, it's much easier to roll forward and roll back any content that you have you're getting errors with by just versioning the URLs that you have. So in this case, you can add a version ID, or if you want to obfuscate it a little bit more, you can add a file size or an MD5 sum. If you are using MD5 sum, you will want to enable query string forwarding to your origin. Reminder when you're using your cache behaviors to minimize the forwarded values as much as possible. As you saw with how we created our cache keys, any additional headers will actually get added to your cache key, and so they will dramatically reduce your cacheability. And if you forward all headers to your origin, we effectively cache nothing. It's a full proxy mode to your origin. When in doubt, check the logs. Enable CloudFront access logs, and here are kind of the standard Nginx and Apache logs with our request IDs in there. You can even come up with your own request IDs, but for anything that you're doing with troubleshooting, it's always helpful to have the request ID, and if you do have to open a support case with us, we'll usually try to know what your request IDs are, just so that we can help dive into exactly what your users are having problems with as well. Key takeaways. Remember to set your cache control headers. That does give you a lot more control over what we cache and for how long. You should also be creating cache behaviors. You can cache dynamic content with a TTL of 0, and so that you can reduce the load to your origin by having us just send conditional gets down. Forward only what you need, version your assets, and please log your request IDs. And now I'll give the floor to Anton.
Hi, everybody. My name is Anton Radlin. I'm an engineering manager with CloudFront, and I'm going to talk to you about measuring application performance with RUM. Oh, could you guys hear that first, Brian? All right. So, before we get into that, let's just break down a few of the things that we're going to discuss here. So, we're going to talk about synthetic monitoring as opposed to RUM, which is real user monitoring. And we're also going to talk about what that means in terms of baselining your performance and gaining situational insight. So, what is synthetic monitoring to start with? I like to think of that as you artificially generating traffic to either your origin or your CDN to determine what is the performance and availability of your application. So this is outside of the regular processes that your users are going through. So what are some of the pros of this? You can get consistent signal as to the health of your service. It's easy to set up generally. This can be as simple as spinning up an EC2 instance in every region, setting up a curl on a cron job every 5 minutes that's detecting what the status code is of your application. Another application of this can be baselining your performance. So what you can do is use this information to say, I'll deploy to 9 different regions and determine from Germany, Japan, from US East, here is the baseline RTTs and throughput that I'm able to get from my application. One thing to note here is that I'm going to be talking about how you do this from a browser perspective generally, but you can get this kind of information for synthetic monitoring from something, say, an SDK, or there are many other applications like that, and I'm actually pretty passionate about this, and I'm happy to discuss more ways that you can use this after. So that's the pros, but let's talk about the happy case and then the sad case when you're using synthetic monitoring. So in this case that I'm actually describing here, we have, we've set up 9 different endpoints where we're doing the synthetic monitoring from. We're collating all of that data. We're aggregating the availability of our service. Now, the problem with this is that you're only testing what you know about in your application. So you're going to go, there's no way for you to possibly enumerate every single way that a user is going to use your application. So when you're using synthetic monitoring, you're really just getting a baseline for how your application is performing, how it's generally available. But in terms of network connectivity, if you look at this user here, he's connecting to your application from, say, South America. All of your endpoints around the world are saying, hey, we're green, we're 100% available, great performance. But in actuality, he has no network connectivity to actually reach your endpoint. Now, you're not going to detect this because you don't have anything running from where your end user is actually reaching your application from. So some of the cons that you can see there are that the network path is going to be completely different from your synthetic monitors than it is from your monitors that you might get from real user measurement. Not to mention that the special cases and snowflakes that you might have in these scenarios are also going to be very different for every end user that's using your application. So, how do you feel about RUM? I love it. I love it in many ways. We use it at CloudFront. In fact, we use synthetic monitoring at CloudFront as well. But we really rely on real user measurements because to us, that's a real indication of how our customers are using CloudFront and what the performance and availability is that they're getting. So how is this applied? In this scenario, I'm going to talk generically about browser performance and availability, but there's many other applications. So generally, these are injected scripts into web pages which are actually timing the resources that are being loaded for your application. These are then sent back to some collation service or some aggregation layer that's actually going to generate some stats for you to be able to look at. There's many RUM providers out there that can do this, but there's also many ways that you can actually do this yourself. So what I'm going to do next is just talk a little bit about if you wanted to implement it yourself, what are some of the things that you could actually look at or find or resources you could look at to actually be able to do this yourself. So what can RUM tell you? What I have up here on the board is actually something that you can find in many different places. It's just the resource timing API. These are some of the different events that you can trigger your monitoring based off of. So I'm not going to go through all of these, but let's just cover a few important ones. What you see there around app cache, you see the fetch start. So that's an event that actually is generated when it's looking in your application or your browser to determine if it's actually in your cache. And what's important about that is that this will not necessarily result in a request to your origin. As Sheree was saying earlier, you can actually set smax age and max age to determine what's actually cached at the browser and what's cached at your CDN or in your origin. So if it doesn't get past the fetch start, you may see that reflected in the metrics that you're gathering. Another important one here is response start and response end. So response start is what people typically think of as time to first byte or first byte latency, which is something that people index on to determine what the actual performance is of your application. It's an important one, but it's not the only one. What we like to look at as well when we're looking at our own metrics is response end, because throughput ultimately is one of the biggest performance boost that you're going to get from a CDN. And you, depending on your use case, are going to find that important. So let's actually dive into an example. I actually just pulled out some trivial examples of looking at websites and going into the network tab. And let's talk a little bit about what we're seeing here and what some of those optimizations can be. So if you look at the example that I have here, this is just the connection portion of a request made from the browser. This is for an object on a random website. So you'll see the queuing, stalled, and blocking time are generally the track time around proxying requests, or if you have head-of-line problems with HTTP 1.1, you may see that reflected here. In this request that you see here, that's a really low time, so not much to say here about optimizations there. Next, we look at DNS lookup. Once again, really low, 1 millisecond. Super low, that probably means that the user already had that in their local resolver cache. Then we have the initial connection time. And what's interesting about this is that it actually makes up more than 90% of the entire connection of this request. And that includes SSL negotiation and the TCP connect time. So that's really interesting because that's a total of 74 milliseconds. If you saw that in your stats as you're collecting your run measurements, you have to look at that and say, okay, this seems like an interesting place that we can actually optimize for, which we'll talk about in a minute. So let's look at the whole request now. What we have here is both the connection time and the request time. When you look at the request time below, you'll see things like request sent, which is the actual time it takes for your browser to send that request to your origin. Then you have time to first byte. Time to first byte here is 41 milliseconds, which makes sense because our connection time was, it looks like the TCP connection time here was around the same amount of time, which means the first byte was actually served very quickly from the origin, but most of the time was spent in negotiating and RTTs. And lastly there, you have content download, which you can translate into throughput, but is essentially the time to last byte. So we'll talk about some specific things that you might want to change when you see things like this in a moment. One other thing I wanted to talk about here, just as an example, this is not necessarily an example of head-of-line blocking, but this is the impact to your latency that you could see if you had it. So if your time to first byte for each one of the objects on your page, for instance, was 100 milliseconds like this one was. In HTTP 1.1, there's pipelining, but it's not fully multiplexed, so you're actually going to end up potentially sequentially requesting objects. And if each object is 100 milliseconds of latency and across 100 objects on the page, that adds up very, very quickly. So what can we do about things like this? Some of the key takeaways that you can actually look at this is evaluate your user base. In the first example, we talked about how the round trip time and TCP negotiation time was actually 70 milliseconds. So you need to understand, where are your users? Do you need an origin in US East 1? Do you need an origin in Sydney? Do you need an origin in South America? These are all going to make a big difference when you're actually establishing connections and serving content to users globally. So it's really key that you understand, where are your users. The second thing is know your data. This is super important. In the example that I showed, it had a really, really low content download time, which means it was a small object in this case, given the RTTs that were probably there. So in another case, you could be looking at video downloads, in which case your total TCP connection time is not going to impact the overall video stream that much, because ultimately you're going to be impacted by things like your congestion window and the available throughput from the machines that they're connecting to. So all of these things are going to show up when you're looking at real user measurements, and it's really important that you understand what that data is, where are they, and how you use it. So how can you optimize some of this stuff? Use CloudFront. That's a starter. We're globally. You can use us to actually optimize all of these things. I'm pretty sure I looked at all of the requests that I looked at, and they weren't using a CDN. So that's super important that you look at that if connection time is really important to you, as well as throughput. Bring your origin as close to your end users as possible. It's super important that when they're connecting, that you have something close to your users. I can't say it enough. That's why we have CDNs. In lieu of using a CDN, make sure that you have your origin as close to where your target demographic is actually going to be. The third thing is HTTP2, which CloudFront supports now. And that will actually help you tackle that head-of-line blocking problem that I described earlier. as you'll be able to actually parallelize all of the requests you're actually serving from your origin. So lastly, here's a few best practices as you're configuring RUM. I've encountered some of these mistakes as I've talked to customers over the years. Make sure that if you are implementing RUM, that you are monitoring the things that are actually critical for your application. So in the case of a website, don't just monitor a single JPEG at the bottom of the page. Monitor your index page. Monitor your CSS if that's important to be able to actually structure the page. In the case of video, make sure you're actually monitoring the video manifest. Are you able to even find the fragments that are necessary to serve your video? And in critical page loads, you can actually monitor the entire page load time and determine, is it taking longer for some users? Is it actually available? Are there some assets missing? These are all possible to get from RUM. And lastly, which I'm open to talk about afterwards as well, first byte latency is not always the most important thing. I know that some people over-index on that. And I just wanted to say, it's know your data, because it's going to be different for every different user. So next we have Efrain coming up.
Hello, my name is Efrain Fuentes, and I am an enterprise solutions architect with AWS. So today I'm going to talk about how you can stop malicious viewers using Amazon CloudFront and the AWS Web Application Firewall, or WAF. And so specifically, I'm going to cover 4 best practices on securing your CloudFront distribution that you can implement in your own AWS environment. And the 4 best practices I'm going to be talking about is 1, leveraging AWS WAF with preconfigured protections. So preconfigured protections is a solution that we developed to help you kind of get started with WAF. And we'll talk about the architecture of the solution and dive a little bit deeper into some of the rules that are part of it. Next, we'll talk about configuring CloudFront to serve private content. So serving private content within CloudFront is actually a 2-step process. So we'll walk through both of those steps. Next, we'll talk about automating security response by using services like AWS Lambda, SNS. We'll walk through a couple of examples just to give you an idea of how that would look. And then lastly, we'll talk about leveraging AWS Certificate Manager for SSL, TLS certificates, both for your CloudFront distribution and for your ELB origin. So AWS WAF gives you control over which traffic to allow or block to your web applications by defining customizable web security rules. So the service was released about a year ago, and since then we've added important capabilities like CloudTrail integration, new match conditions, and then IPv6 support more recently. We've also added AWS WAF to the list of PCI DSS 3.2 Level 1 compliant AWS services this year as well. So AWS WAF includes some native rules for things like cross-site scripting and SQL injection. However, one of the most powerful features of AWS WAF is the capability to allow you to create your own custom rules based on the traffic that you're seeing. And it's a great capability. Customers use it all the time. However, sometimes it's difficult to come up with a web application firewall strategy and create these custom rules, especially if you don't have dedicated security teams that you're working with. And so what we did is we developed a solution to simplify this process that uses a CloudFormation template and automatically deploys a set of AWS WAF rules that are designed to filter common web-based attacks. And so when you deploy this CloudFormation template, you can select which of the rules you want to enable. And then you also set some parameters for some of those rules that are specific to each of those. So I'm going to walk through this architecture at a high level, and then we'll dive into the 3 customized components of the solution that are implemented through Lambda functions. So the solution includes 6 different components. The first one is a bad bot and scraper protection component. And so the way that is implemented is through an API, Amazon API gateway endpoint. It's essentially a honeypot that you embed into your web application. The next two components, the SQL Server injection protection and the cross-site scripting protection, are two native rules with AWS WAF. Then we have the HT flood scanner and probe protection. And so that's also implemented through a Lambda function that parses the CloudFront access logs as they're delivered into S3. And then the last component of the solution here is the known attacker protection. So again, this is a Lambda function that is triggered by a CloudWatch event on an hourly schedule that goes out and obtains IP lists, queries third-party IP reputation lists, and then takes those in and updates AWS WAF based on that. So let's go into each of these custom components. So the first one is the access handler. And so the access handler is what protects you against the bad bots and scrapers. And the way that this is implemented is through an API gateway endpoint that you essentially embed within your web application. And then once you embedded it within your web application, you update your robot.txt file to explicitly disallow that particular endpoint. When a scraper or a bot accesses that page on your site and tries to hit that API gateway honeypot endpoint, it triggers the AWS Lambda access handler function, and that access handler function then updates the IP block list based on that activity. So the next component I'll talk about is the log parser component. So the log parser component, again, is implemented through a Lambda function. And the way that this works is as the Amazon CloudFront access logs are delivered within the Amazon S3 bucket, it triggers that AWS Lambda log parser function that examines the logs and then determines, based on that examination, whether the IP list should be updated to block against those requests. And again, this is all extensible, right? So we have this configured and ready to go for you, but you can extend these Lambda functions as you need to and customize them further. The last component I'll talk about is the IP list parser. So this component here, it uses a Amazon CloudWatch event that's scheduled to kick off on an hourly basis. And that triggers the Lambda function that goes out and fetches IP lists from 3 different sources. So it currently accesses the spam house do not route or peer list, and then the extended do not route or peer list. We also pull IPs from the Tor exit nodes list, and then the proof point emerging threats IP list. So those are the 3 that are part of the solution. But again, if you have other requirements, if you have other providers of these types of reputation lists, you could certainly implement that or extend this to accommodate that. And so the solution is available. You can download it off our site. I have the URL here, and we'll provide the presentation so you can get to it. Again, it's a CloudFormation template, so there's a lot of points of customization before you deploy it, but it's a very quick and easy way to get up and running with some of these customized rules to protect your CloudFront distributions. Okay, so the next best practice I'll talk about is serving private content or configuring CloudFront to serve private content. And again, it's a 2-step process, right? So the first part of this process is to restrict the origin access. The second part of the process is to use signed URLs or signed cookies to protect your content. Now, you may not have a need to do the second part of it, but restricting origin access is the best practice regardless of if you have content that you want to explicitly protect. So there's 2 ways that you could do this, depending on whether you're using S3 as your origin or whether you have a custom origin, whether it be on EC2 or even in your own data center. So the first way, if you're using S3 for your static content in your distribution, then you can go ahead and use origin access identity to prevent direct access to that S3 bucket. So that prevents viewers from circumventing the rules that you've built within WAF and within CloudFront and going directly to S3. Likewise, if you have a custom origin, if you have, you're using an ELB on Amazon or you're using something at in your own data center, you could use the list of CloudFront the IP range of the CloudFront edge locations to whitelist those at those origins and only allow access from that list of IP addresses. And again, that prevents users from directly going to your origin and circumventing the WAF protections that you've implemented within your distribution. The second part of private content is using signed URLs and cookies. And again, you may not have a need for this, but if you do, there's different things you could do with each of these. So with signed URLs, you add the signature in the query string, and essentially both signed URLs and cookies are used to protect either a specific piece of content or a group of content items within your distribution. So with signed URLs, you add the signature in the query string, so the URL is going to change. Signed URLs are used mostly for restricting access to individual files, not large amounts of content. Signed cookies, again, the URL doesn't change with signed cookies, but you typically use signed cookies to restrict access to multiple files or an area of your application. So the next best practice here I'll talk about is automating security response. So we talked a little bit about this in that first example, right? So that's an example of how you can automate the updates of your WAF rules. This is another example here, and this covers the case where you have an origin that you are only whitelisting the CloudFront edge location IPs to. And so this gives you some automation around that. And again, this is another solution that's on our GitHub site, so you guys can definitely access it and download it. The URL is down here. And so what this solution does is essentially it updates the security groups based on the changes in the IP list of the CloudFront servers, right? So whenever that changes, there's a Lambda function that subscribes to this SNS topic. The SNS topic then triggers that Lambda function. Lambda updates your security groups with the latest whitelist, so you don't have to manually keep track of when those IP address change and have to manually do this. And the last best practice I'll leave you with here is leverage AWS Certificate Manager for SSL and TLS certificates. So ACM allows you to provision and deploy TLS and SSL certificates at no additional cost. And then you can associate those certificates with your CloudFront distribution or your ELB origin. And to get up and running with AWS Certificate Manager, it's pretty straightforward. If you're already using CloudFront, most of this is already done. You have a CloudFront distribution, right? But if you don't, then you would set up your origin, whether it be an EC2 origin or an S3 bucket. Next, you set up your CloudFront distribution, set up your caching rules, set up your origins within your CloudFront distribution. Once you're done with that, then you can request the certificate through either the console or through the API or CLI. And so once you have that certificate, the last step is really just associating that certificate with your CloudFront distribution. Once that certificate is associated with your CloudFront distribution, it gets pushed out to all the edge locations, and then we use that to terminate SSL at the edge. All right, so the key takeaways here, leverage AWS WAF, more specifically, leverage AWS WAF with preconfigured protections to give you a good starting point. Secure your origin and content. Preventing direct access to your origin is always a best practice, whether you use signed URLs or signed cookies or not. And then the last piece is automate security response by using some of our other complementary services. Great. Cool.
Mike? Great. Thank you very much to Cherie, Anton, and Efren for taking the time to share some thoughts on best practices with CloudFront. And really thank you all for coming to reInvent. And please do complete your evaluation so we can learn how to make this a better conference. Have a good day.